Okay, perfect. So yes, I will be talking about GRACE data processing and two main tasks we have to perform before downscaling, which is filling data gap between GRACE and GRACE follow-on, and also filling some smaller data gaps. And the later part is downscaling, which is enhancing the spatial resolution of GRACE, which might be too coarse for some regional analysis. Yeah, but I will start with a few words about basics of the GRACE mission and what exactly is measured by GRACE satellites. So in general, GRACE mission measures temporal changes in Earth gravity field caused by changes in global mass distribution, like, for example, river flows, some distribution of water on land, and also in atmosphere and oceans. There are a lot of processing steps from original GRACE measurements of changes in distance between two identical satellites to the final product, which is terrestrial water storage. But this is not our goal, because there are a lot of processing centers that process GRACE data and provide us some nice maps of terrestrial water storage variations, which we can use for our analysis. And so in general, terrestrial water storage, which is the final product of GRACE measurement, reflects changes in Earth gravity field caused by variations in mass distribution. And the unit of this variable is centimeter or millimeter, so that this data can be compared with similar variables provided by land surface or hydrological models. So the most important thing is that GRACE gives us a picture of the total changes of water in all storage components, like water in rivers, groundwater, soil moisture, and so on. And another important aspect is that GRACE actually does not provide the amount of water, the total amount of water at a given location, but time variations of terrestrial water storage, which are deviations from some long-term mean. We can compare terrestrial water storage from GRACE with that obtained from hydrological models, but one key difference between these two data sets is that GRACE provides us change in total water storage in all these components together, while typically hydrological models provides variables separately for each component. And most often, hydrological models do not provide us groundwater. That is why, by combining satellite gravimetry and hydrological models, we can obtain so-called satellite-based groundwater storage, assuming that total water storage, as observed by GRACE, is the sum of groundwater storage, which is our unknown, and water in other components, which are provided by hydrological models, like water in soil moisture, snow cover, and biomass. But this is somehow a simplified approach, well tested in different articles for different regions, but still simplified. And if we have to obtain most reliable estimate of groundwater storage from satellite observations, we need to take into account local hydrological conditions And this will be the topic of Tatiana's presentation today. But I will now tell you some few words about GRACE data details and processing. So in general, for regional studies, it is recommended to use so-called MASCON solutions. I will not go into much detail, but the general idea for MASCON solutions is that the area of the whole globe is divided into equal area blocks called MASCONs, which are typically rectangular or spherical in shape. And in each of this block, terrestrial water storage is computed separately from direct measurements of range rate between two satellites. So, for example, for CSR solution, the area of the Earth is divided into a lot of MASCONs which are hexagonal, and they have diameter of 1 degree. And in each such a block, we have one value of terrestrial water storage. But to facilitate regional studies, usually values computed in MASCONs are then resampled to regular grids. And in the case of CSR, terrestrial water storage anomalies are given in 0.25 degree grids. And we used this newest solution from Center for Space Research, which can be downloaded from this web page, and the data format is netcdf. So it is very simple to download the data because there is only one link and one data file for all epochs. So just by simple clicking on this link, you will download the data, which is quite time consuming because of the size of file, but still you do not have perform any additional processing apart from downscaling and filling data gap. So yes, here you can see an example of time series of terrestrial water storage for an example data point. So by design, GRACE are monthly data, which means that after a month, we have a full coverage of globe with observations. So monthly temporal resolution is best for GRACE, and in ideal case, for each epoch, we have terrestrial water storage anomalies as an average of all observations collected throughout the entire month. And the reference date for this epoch is usually exact middle of month. But sometimes it is not the case because of some gaps in measurements, some technical issues. So yeah, let's zoom on this plot to show a few years only. So we can see that there are some irregularities, like data gaps, for example. And yeah, I have to say that each vertical line here represent exact middle of the month. So we can see, for example, here that in the case of this observation, it is not related to the middle of month as it should be. And sometimes it is because a few days at the beginning or at the end of a monthly interval are excluded from the solutions because of some technical issues, some losses of observations. That is why the center of observational period is shifted slightly away from the middle of the month. And another bigger problem is while we have several days of no data, which results in some data gaps where we have missing 1, 2, or 3 months of data like here. It is because of temporal problems with measurements. And the last issue with GRACE data is 11-month gap between end of GRACE measurements and beginning of GRACE follow-on measurements. And this gap should be filled with some methods, maybe not simple interpolation, but some prediction maybe. So for this purpose, we used some simple method of prediction based on autoregressive integrated moving average. So the idea is to make a prediction using ARIMA model and historical data, all historical data before the data gap. So first of all, we removed linear trend from the whole GRACE-based series, and then defined the ARIMA model, which was then fitted to the series. And based on the estimated model, we performed predictions of the 11 missing months. And then we restored trend to obtain the whole series of GRACE, data gap, and GRACE follow-on series. And then we also made interpolation the series to the mid-month timestamps, which enabled us to fill occasional data gaps of 1 or 2 months within the GRACE and the GRACE follow-on periods. So this is quite a simple approach, which is reasonable for a series with strong seasonal signals. But in terrestrial water storage, we have such strong seasonal signals. So we assumed this is some good methods for simple but quite good method for filling missing data. So this is the example of our approach. So in green we have original GRACE and GRACE follow-on series, and in red there is a predicted fragment. And yeah, we also performed some uncertainty estimation of gap filling, because we cannot compare predicted values with observed one, because there are no observed values of GRACE for this period. So what we have done is to introduce artificial gaps in GRACE records, and then to fill these artificial gaps with the same method as in the case of real data gap, and then to compare original and predicted values. So for this purpose, we selected 3 different artificial data gaps in 2005, 2007, and 2010. And this is the effect of our data gap filling. So we can see, for example, that in the case of 2005, there is a quite good fit to the observed data. So we can assume that when there are no rapid increases or decreases of water storage, for example, Here, so the model is quite well, but in the case of this period, we observed a sharp increase in terrestrial water storage, which was connected with heavy rains in Poland that time and some flooding. And we can see that for this purpose, in this case, the model is not so good. But still, this is some method for filling missing points. Then we calculated root mean square errors and mean absolute errors for this artificial data gaps to quantify uncertainties. And for each grid cell, we calculated this metrics for each of 3 data gaps, and then averaged it to obtain a single value for each grid. And the final uncertainty was computed as an average of values for 3 gaps and for all grid cells. So here are these values. So these metrics were computed for only 11 points because the gap was 11 months. So in general, as expected, we see that in the case of 2010, the error is highest. But in general, the mean uncertainty for the whole area of Poland is around 3 or 4 centimeters, depending on the parameter. But yeah, these metrics are computed for only the period of grid cell. But if we compare the full terrestrial water storage series for all data point, if we compare original data and data with filled artificial gaps, naturally these errors will be lower, below 1 centimeter. And in general, correlations between original and series with artificial data gaps are very high. So in general, if we have long enough time series, the gap filling procedure has not so much impact. So maybe it's a simple method, but still it works quite nicely. And here is a spatial distribution of gap filling uncertainties. So in general, we expect higher errors in the northern part of Poland because of land-sea boundary, and also in the southwestern part where there are mountains. So in general, uncertainties of GRACE measurements are also higher in mountains. And now our second task, which is downscaling of GRACE data. So as I said previously, GRACE CSR Mascon solution provides us data on 0.25 degree grids. However, this is only data sampling. It is not a real spatial resolution, because spatial resolution is an effect of many factors like sensitivity of GRACE satellites, but also size of Mascon and some model errors and filtering effects. And it is said that the real spatial resolution of Mascon data is around 150 to 200 kilometers. So to picture this for you, here is an example of terrestrial water storage map for Poland for one epoch. So yeah, these data are originally provided in such a small grid, but yeah, here you can see 0.1 degree grid, and you can see that actually there are a lot of neighboring grids with the same value. And this is the effect of that originally this solution was computed in a hexagonal mascon of the size of around 1 degree. So that is why neighboring small grids has the same values, and this is why we need to downscale GRACE data to obtain reliable information in a denser grid. So yeah, a general idea of downscaling is to use high resolution predictors which are connected with water storage dynamics, like for example precipitation, evapotranspiration, runoff, soil moisture. And then we also have to have some methods that could capture relationships between GRACE data and these high resolution predictors. But it is important to have these predictors on higher resolution than GRACE. So in principle, there are two main steps to downscale data. First is to use some method, like for example, machine learning algorithm to determine relationships which are probably non-linear between high resolution predictors and coarse terrestrial water storage from GRACE. And then after training and building this model, we can use this model to estimate terrestrial water storage from GRACE on a finer dense grid. So yeah, of course, the first step of the downscaling is data preparation, because we have to have all the data, including predictors and target GRACE, in the same grid size and in the same and for the same moments of the time. So as Anya said previously, we used 4 predictors. Almost all of them were monthly data, but there were some differences in grid size. So we tested few sampling grid sizes in our downscaling approaches. And then after resampling all the data to the same moments and to the same grids, we have to perform model training to let the model learn the relationships between low resolution GRACE data and high resolution predictors. And for this purpose, we chose random forests, because yeah, I must admit that it was our first task with the use of machine learning. So we started with some quite simple method, which is random forest, but at the same time, it offers an ability to capture sometimes complex relationships between variables. And this method is also well tested in different works related to data downscaling for different regions. So that is why we chose random forests. And yeah, we perform training for each month separately. And yeah, in the training, we randomly split the data into training and testing subsets. to ensure performance assessment. So 80% of the data was used to train, and then 20% of data was used for validation. And for the model training, we used MATLAB software, because MATLAB has a lot of built-in functions for machine learning. But of course, probably Python also has some tools for this. I used to work with MATLAB, that's why I used MATLAB for our downscaling. So these are basic parameters of regression trees, like a number of regression trees and maximum leaf size. I tested many variants of these parameters, but based on what I found in other works, I assume that these parameters should be fine for our purpose. So then, after training the model, we use this trained model to apply it to the high-resolution predictors to estimate downscaled terrestrial water storage from GRACE. And our target spatial resolution was 0.1 degree. Yeah. And finally, we performed some validation, which was based on test data and based on comparison of terrestrial water storage before and after downscaling. So now I will show you some example results from Book River Basin. So first of all, here are time series of our predictors: soil moisture, runoff, evapotranspiration, and precipitation. And our result is downscaled terrestrial water storage. On the top panel, we have time series for the Book River Basin before downscaling, and here are series after downscaling. So what we can see that despite we have data for almost 120 different points, we do see that for this area we have only maybe 10 unique time series, so that it was visible on the map where I showed you that neighboring grids has the same values. And after downscaling, actually, we have more unique values, but still these series are almost the same as this series. So the variability of the series is not so high, but still we have more unique values for the area. So here are example maps of our predictors and terrestrial water storage before and after downscaling. Maybe this approach is not perfect, because we can see, for example, that in winter months, actually evapotranspiration is 0. So the real number of predictors for this month is not 4, but 3. So maybe we should think about adding additional predictors to perform better downscaling. And also we work on improving the quality of river runoff, because this one is based on data from 30 points, I think. So adding more data points should improve the quality of this predictor. So I will just show you a few maps for our downscaling. So yeah, in general, we do see that there are more variability within the area after downscaling. But of course, we can improve this method by adding, for example, more predictors. And random forests also gives us an opportunity to compute importance of each predictor in the downscaling process. So depending on the epoch, this relation is quite different. For example, evapotranspiration has no impact in winter months because it has 0 values for these epochs. But in general, the highest is the contribution from soil moisture, almost 50%. And now results of uncertainty of downscaled terrestrial water storage estimates. So as I said, we performed validation using test data and by comparing terrestrial water storage before and after downscaling. So here you can see time variability of root mean square error, mean absolute error, and R squared for test data in black and final validation in red. So in general, here we can see some epochs with worse downscaling performance, but it is also connected with, in general, worse GRACE data quality because of some technical issues. So it is expected that at this epochs we have higher uncertainties. But for this epochs, we are not sure. Probably there are some problems with predictor data. So this should be verified. But in general, if we average these metrics over the whole period, we do see that the downscaling process is quite well performing, and the errors are not higher than 1 centimeter. And actually, the curves of time series before and after downscaling is quite similar, but the spatial variability is higher. And yeah, so after downscaling, we used this downscaled GRACE data to compute satellite-based groundwater storage. And this is the topic of Tatiana's presentation. And as the next step for improving this downscaling quality, we think that it would be good to add more predictors, more high-resolution predictors, like, for example, digital elevation model or specific yield information. Also, we have to improve our runoff data to improve more monitoring points. And since soil moisture is most important predictor, we think that it would be good to use this data with higher spatial resolution. So yeah, actually that is all what I prepared. So thanks for your attention.
Hey, this looks wonderful. Vitalis has a question.
Hello, Steven. I have a question. Yes, so you already did some downscaling on your own. I wanted to ask, how accurate was that model? Do you have any statistics on how accurate how accurately it was predicting downscaled GRACE?
So we made some accuracy performance only based on test data, as you can see here. Okay. And based on comparison of terrestrial water storage values before downscaling and after downscaling, which is this red line.
Okay, I see.
So average values for the Bok River Basin is here. So it's below 1 centimeter. I know that machine learning probably offers some other metrics for model assessment.
No, like the same ones.
Okay.
Okay. So, and you were using only those predictors. You were not using like historical GRACE data, like previous months.
No. I just for each epoch, I've looked into spatial relationships between variables. So for each month, I performed model training and then prediction. So I'm not sure if this is a good approach, but I started with this analysis.
So you just took 1 month and created a model for the entire area for that 1 month.
Yes, exactly. So,
Okay. Because till now, well, I'm getting, when we are using time series for each cell, so we are getting way worse results, I believe. Maybe not way worse, but slightly worse statistics. So I'm just curious on your approach. So yeah, you will be probably will be sharing your slides with me. So
yes.
I would like to analyze it a bit deeper. Okay, thank you, Justina. Ilya is writing something.
Yeah, I think like 4 questions, one of them along the lines of what Vitautas just asked. Actually 2 of them. But the first question is that gap between GRACE and GRACE FO, it's sort of well known. Is there any general solution that is recommended by NASA or somebody like that? And why each project has to do it?
Actually, there are no recommended method for this downscaling. There are a lot of existing approaches, both based on some prediction methods or by using another data sources like from hydrological models. But I think actually, if you have a long enough time series, the impact of this data gap filling is not so high. So sometimes assuming only seasonality is quite fine. But
Yeah, I just thought that since this is like a well-known gap, somebody would just solve it and get done with it.
And what I will take into account is maybe not to, because I made a prediction in the future based on GRACE records only. So maybe better approach is to perform prediction to the future based on GRACE data and then prediction based on GRACE follow on to the back and then maybe make some mean of these 2 predictions. I'm not sure.
Yeah, exactly. You can just ignore the gap. Exactly. So the second thing is you move from hexagons to rectangular cells. One option would be just to stay with more granular hexagons. Did you consider that?
You mean this hexagons, right?
Yeah.
So actually, data in these hexagons are not available because by convention, processing centers provide data in regular grids.
Okay, rectangle. Yeah, that is sort of not very intuitive because they could have just stayed with hexagons and have fewer problems.
Yes, but giving the cross original spatial resolution, I'm not sure if this has a meaningful effect anyway.
Yeah, and the last 2 things is basically what Vitautas was already talks about. If we can look at at the notebook and perhaps done cross validations, just to compare this across models, that would certainly help. Because when you sample different locations in do the spatial sampling, you may end up with downscaled cells that have pretty much identical values if they're close to each other, being in training and testing, and that's something we may want to separate. And I see that Vitaldis and Argo have their hands up, so please feel free to.
Argo, you first.
Yeah, okay.
Thank you, Justina. It was a very nice presentation. I think your fit is already very good. There is both the not the downscaled and I was wondering the same thing as Vitautas was asking about the using past data in a sense that the water balance from the last months or several months pretty good fit, so there is no need maybe, but this could be the way to think and try to improve the data perhaps. But I think you didn't use these previous months data, right?
No, so I only used this for predictors. So actually, the trained model only took into account spatial relationships, not temporal relationships. If the, for example, terrestrial water storage is have a lag of 2 months compared to other predictors, it is not captured by the model. So probably including some temporal dependence could improve the model performance.
Well, in principle, if you don't use the data from previous month, there is no point to fill the gaps in data, in graceful data. Because, well, if you use just 1 month data only and not related to previous periods, then well, you just leave these a few months out in the overall analysis. That's also one option to go, because when you predict something, you try to fill something, you introduce also some unknowns that may or may not improve the overall fit.
Yes, thank you.
Without us.
Yeah, so I have just more general questions. I actually found. What do you think of the data sets and databases of the same GRACE data, which is very heavily processed and modeled already? Because I found one a fusion, I think, of GLDAS and GRACE data, which actually gives daily groundwater storages and terrestrial water storages for entire globe, and the article associated with that. What do you think? Have you ever checked that? Is it a reliable source?
I think yes, each reliable, each combination of GRACE with some model could be reliable. But I think that most of this data, I'm not sure what data set you are talking about, because there are a few data sets of combination of GRACE with hydrological models to obtain the groundwater storage. And I think that GLWS, this is something like, is it GLWS?
I don't have that at hand. I will send you maybe an email just to show you, because I'm just interested, because we were always talking about monthly data, and there was like already modeled some in grids 0.25 that. So yeah, so just your opinion. It would be great if you give one. Thank you.
So if you could send me this data name or link, I will check it. But I think at least GLWS data is quite reliable. It is for the whole globe, I think, but still its resolution is 0.25, not 0.1. But 0.1 is, I think, our target. So I assume that for the whole globe, it is not possible, or it is very time consuming to compute such downscaling for the whole globe with 0.1 degree. So that is why I didn't find any downscaled data for the whole globe with resolution better than 0.25.
Okay, I see. Okay, thank you, Justina. Very nice presentation.
Thank you.